Hello and welcome to Texas Instruments VCE Mathematical Methods Term 3 Revision Series. In this webinar, we're going to look at some exam-style questions, Part 2, Calculus, and my name is Peter. The program for today, find the location and nature of stationary points, and rather than using the calculator application, for that we will use the notes application. Secondly, we'll look at a question type where we need to analyse whether in fact we need to find the derivative of a function or not to answer the question. And what TI-Nspire provides is an increased range of possible solution methods. And thirdly, we'll look at an example from integral calculus, the average value of a function. And again, rather than using the calculator application, we'll use the notes application, and we'll attempt to show you that the notes application will hopefully become a very good friend of yours in the exam too. So let's get started, and we'll look at a typical question type where we're asked to, first of all, find the derivative of that function, and then secondly, determine the coordinates and the nature of the stationary points on the graph of G. First of all, a point about notation. The first R there is indicating that the domain of G is R. So G has a domain R. Now this second R is not the range. It's a set called the codomain. So function G has a domain R and a codomain of R. Now, there is a subtle difference between a range and a codomain. The codomain is the set of values that could possibly come out as part of the definition of the function. The range, however, is the set of values that actually do come out of the function. So to think very simply, if we had f of x equals 2 times x, and we set the domain and codomain to be positive integers, then the codomain, obviously, by definition, is positive integers, but the range, because we're taking each value of x and multiplying it by 2, the range would, in fact, be even positive integers, showing you that the range can be different to the codomain, and, in fact, the range is a subset of the codomain. So I don't want you to gloss over this notation, and make sure you understand it. Okay. So moving right along, it's well within our capabilities to be able to write down the answer for g dashed of x. Using the power law for differentiation, you can see that g dashed of x is negative 3x squared minus 6x plus 24. And we can certainly graph this, etc., and determine the coordinates and nature of the stationary points graphically, algebraically. And this is what I was saying, that TI-Nspire increases the range of possible solution methods. In the exam, I also want you to think mathematically as you're doing such questions. Now, I know that that sounds like sort of a Captain Obvious type statement, but this cubic is a negative cubic. And so if it's got two stationary points, you would expect the first one to be a local minimum and the second one to be a local maximum as you're moving towards the positive direction of x. So in other words, it's always a good thing, a good attribute to have to be able to anticipate answers by looking at the function that you're dealing with. Okay, let's show you an example of a notes application here. So a notes application have these wonderful objects called math boxes. To insert a math box into a notes application, you simply press Control M. On this screen, anything that's in blue is inside a math box. So that function there is in a math box. The derivative there, that's in a math box. Now, what I'm illustrating here is that we can set up notes pages that include or embed within them solution recipes to guide you through step by step what you should be doing to answer the question. So step 1 says assign f of x. So, you can define. So defining, storing, and assigning are very close to the same thing. The assign command is located or found by pressing Control and then the symbols template. So the assign command is a colon equals, and you can see a little blue colon equals there above the symbols template. So I've assigned f of x to be that cubic. Go inside the math box and press enter, and the message we've received is done, and it illustrates to us that, okay, the function has been assigned. If the function is really difficult, TI-Nspire might sometimes say, well done. So watch out for that. Moving down to step 2, it says find f dashed of x. So this is the recipe for finding the location, first of all, of any stationary points. So we click in on the math box and we press enter, and the derivative there, as we anticipated, is negative 3x squared minus 6x plus 24. So we've assigned the function, we've found the derivative. Moving on down, step 3 in our recipe is we need to solve f dashed of x equals 0 for x to find the x coordinates of the stationary points, the points where the gradient is 0. Now, you may have used the solve command in the past. I'm going to use another command that is part of the algebra menu, and it's called the zeros command. It does essentially the same thing, however, the output is slightly different. When you use the solve command, you might get something like x equals negative 4 or x equals 2, something like that. With the zeros command, what happens is you get your x values as a list, okay? And what I've done here in step 3 is I've said, well, okay, there's a couple of steps going on here. We're using the zeros command. We're finding the zeros of the derivative. Now, the zeros command, what you have there is already assumed to be set equal to 0. So that's why you don't see an equal 0. And it's comma x, the independent variable. What I've done is I've assigned whatever values come out of that to be xc. So I'm thinking xc, the c is critical, so critical values. That's a cue that I use. You could use xs, for example, for x coordinates of stationary points. And that's the box there where if there is a domain constraint, now we're dealing with a cubic polynomial, so and the domain was the real, so we don't need to embed or insert a domain restriction. If you needed to, this is the place to do it, and what you would do is you would press Control equals to access the with or the given command. That's the same symbol that's in conditional probability. So we go inside that math box and we press enter. What that is telling us is that there is a stationary point at x equals negative 4 and there is a stationary point at x equals 2. Now, the next math box we're not going to use today. This is if we wanted or if we had to get the x coordinates of stationary points in decimal form. And that's why we've got the use of the approximate command there. So we'll leave that math box dormant and we'll go down to step 4, which says what we do now is we substitute the x values of the stationary points into f of x to find the corresponding function values. So the first one that we're going to find, will correspond to x equals negative 4, and the second one that we find will correspond to x equals 2. So we go inside f of xc, and we see there, therefore, that we have a stationary point at negative 4, negative 88, and a stationary point at 220. So from our knowledge that we're dealing with a negative cubic, we would expect negative 4, negative 88 to be a local minimum and 220 to be a local maximum. Next is a little bit fancy. It's actually undertaking first derivative analysis to demonstrate the nature of the two stationary points. And so what I'm doing is I'm choosing a value of h, which is very small. And what we do is we check the value of the derivative just to the left and just to the right of each of the stationary points. So I've chosen h to be 0.01. That's just arbitrary, but it's small. It's either side of the stationary point, and we press enter to activate that. So what our next three math boxes, these are going to be the gradients. Well, for this one, it's going to be the gradient to the left. So if we click on the math box there and then press enter, that is the gradient of the curve to the left of x equals -4. And this one is the gradient to the left, just to the left of x equals 2. So you can see how the lists are lining up. The first value is going to correspond to -4, -88, and the second one to 220. I have an alternative perspective on this that I worked upon this afternoon that I'll show you in a minute. We would expect the output in this math box to be 0, 0 because we're at the stationary points, and the gradients there at the stationary points are 0, 0. And now we look at both stationary points just to the right of them. We look at the gradient of the curve just to the right. We press enter, and so this one corresponds to, we're looking at -4, -88 for the first number, and we're looking at 220 for the second number. So the way, now this makes sense to me. When we look at the first stationary point, just to the left of it, the gradient is negative, then it's 0 at the stationary point, and then it's positive. So -0, positive corresponds to local minimum. So therefore, -4, -88 is a local minimum. Now we're looking at 220, just to the left of the stationary point at x equals 2. The gradient is positive. Then it's 0 at the stationary point, and then it's negative just to the right. So that goes positive, 0, negative. So that corresponds to a local maximum. So we've been able to determine that -4, -88 is a local minimum and 220 is a local maximum. Alternatively, you can also use second derivative analysis. So if you press enter there, that first number shows you that the second derivative at x equals -4 is positive. So that corresponds to a local minimum. And this second number corresponds to the value of the second derivative at x equals 2. It's negative, and so therefore we have a local maximum. So you've got the choice there. Now, what I was mucking around with just briefly this afternoon before I came on air was to look at a stripped down version of this that also included a domain constraint. So this one is one of the questions on the accompanying student worksheet. So what we'll do is I'll go inside that math box and press enter. So we've got a new function. F of x here is x on 2 plus cos x. You should be able to differentiate that mentally. That should be a half minus sine x. And here what we're doing is we're using our zeros command. So we're setting the derivative to 0 and solving, and we're calling the x coordinates of the stationary points xc. And I've added a domain constraint because in the question, this function does have a domain constraint. X lies between 0 and pi. So we don't want extra solutions floating around. So I've added that domain constraint using the width or the given key. We press enter, and so we've got two stationary points. One occurs at x equals pi on 6, and the second one occurs at x equals 5 pi on 6. So again, note that the output there is a list. We then substitute those values into the function, and our function value is in exact form there. The question in the student worksheet asks for exact form, so that's why I'm not using the approximate command. So we've got a stationary point at pi on 6, and then pi on 12 plus root 3 on 2. And the second stationary point is 5 pi on 6, and then the y-coordinate is 5 pi on 12 minus root 3 on 2. So we need to determine which is which. So we scroll down. We've got our small h value. And here what I've decided to do, and this might suit some of you, rather than the setup I had in the previous example, what I've decided to do is to put the test values all into one list. And so when I press enter, what comes out is, I don't know if you've ever seen this before, so this is a matrix. And so these values correspond to, that's the gradient just to the left of 5 pi on 6. That's the gradient at x equals, sorry, pi on 6. That's the gradient just to the left of x equals pi on 6. That's the gradient at x equals pi on 6. And this is just to the right of x equals pi on 6. And it's corresponding there for 5 pi on 6. And so what we can glean there is that at x equals pi on 6, what we've got is we've got a local maximum, and at x equals 5 pi on 6, we've got a local minimum. So that shows you a more cut down version of such a notes page, and that might suit you. So it depends what you want to do. If you want to set up a notes page that has lots of scaffolding and lots of instructions, then by all means do that. If you don't need the instructions, then you can go with something quite lean like this. So I think that it's really important that you, in conjunction with your teachers and fellow students, develop a nice suite or a nice number of notes pages that you can take into the exam. So study past exams and work out what sort of question types are quite popular, and then write notes pages or construct notes pages for them. And in that way, you might gain some marks quite quickly in the exam, because unfortunately in an exam, time is of the essence. Okay, so we're moving right along. This is the corresponding plot of the curve. And just a reminder, if you wanted to find the coordinates of the local minimum, what you could do there is press menu and then 6 for analyze graph, 2 for minimum, and then move this dotted vertical line to the left of the point of interest and press enter, and then move across to the right of it. And then you'll see minimum come up. You see the coordinates goes to there. Press enter again, and you'll see that indeed the local minimum is at -4, -88. Okay, this one here, this is a question in the student worksheet, which we won't go through here. What's quite interesting, again, it's this idea of what do I expect my graph to look like? Now, x, we've got a product of two functions here. X is an odd function, and e to the -x squared, I don't know if you've studied the normal distribution yet. The curve there, that's symmetrical about the y-axis, and that's an even function. So we've got a product of an odd function and an even function, and just like numbers, odd times even is odd. So we would expect to see an odd function, which we do here, and odd functions are symmetrical about the origin. So it's thinking like that, as well as doing the question at the time, you know, will hopefully add some you know, marks to your final mark in these upcoming exams. Next example, bit of a wordy example here, and I've posed the provocative question, well, do I need to find the derivative? So we'll have a look at the question. So over a 24-hour period at a town H, the temperature H degrees Celsius at time T hours after 6 a.m. can be modelled by that function there. Now that's an inverted parabola. And what I tend to do when I do maths questions is I pick out a couple of special values to get a sense of what's going on. So for H of T there, when T equals 0, I get 144 on negative 18. So that's -8 plus 25 is 17. So the initial temperature is 17. The other thing is that this parabola is in vertex form. So the maximum, because it's upside down or inverted, is going to be 1225. So we can already tell that at 6 p.m. the temperature is 25 degrees, and that's the maximum temperature. There's a corresponding town W, and over the same time period, the temperature W degrees Celsius at time T hours after 6 a.m. can be modelled by that transformed trig function. So again, when T equals 0, cos of 0 is 1, so the initial temperature is at 6 a.m. is 17. And T equals 12 looks to be a special value. So if I put T equals 12 into there, cos of pi is -1. So 21 minus 4 times -1 is 21 plus 4, which is 25. So at T equals 12, what you'll see is that T equals 0, T equals 12, and T equals 24, the temperatures at the two towns are the same. But what happens in the interim? What we can do is we can define another function, d of t, which is the difference of the two. So that's, in this instance, it's h of t minus w of t. We've been kind here. We've omitted the need for an absolute value. And we've asked you here to correct to two decimal places the values of t for which the maximum difference in temperature occurs. Find correct to one decimal place the maximum difference in temperature. Okay, so a rarity for me is a calculator page here. This is the three functions assigned. So h of t has been assigned, w of t has been assigned, and d of t has been assigned to be the difference. And assign is control symbols template. I'm going to come back to that page in a couple of moments. So I'm going to be sort of jumping around a couple of pages here. Here is a picture of the two functions, and it bears out what I was thinking when I was looking at some t values, in particular 0, 12, and 24. We note that the two towns have the same temperature at those times. The red curve is town H, and the black curve is town W. Very imaginatively, I had town H for hot and town W for warm. That shows you how cluey I really am not. So what we'll do now is we can look at this and we can say, well, I think that the maximum difference appears to be probably around about T equals 4. And because there's symmetry about the vertical line T equals 12, there'll be a corresponding maximum difference over here. Now, if it occurs at about 4 here, it's going to occur at 4 less than 24. So we're expecting answers of around T equals 4 and T equals 20. I'm going to come back to this page and illustrate the use of this segment just in a moment. What the question is cueing us to do really is to graph the difference of the two functions, which I've done here, and you get this wonderful symmetric curve, which you can see that has to be T equals 12, where the graph touches the horizontal axis. And what we do is we know from the previous graphs on the same page that we're expecting to see two local maximum. One occurs at, correct to two decimal places, at 3.93, and this one, correct to two decimal places, at 20.07. Now, it looks as though that I'm in float 5. So if you press menu, settings number 9, that'll give you an idea. So you can choose what display digits you want to display. I'm not overly keen on too many, but you don't want to go down to float 1 or 2, particularly if there's the occasion where questions, the answers of which are asked to be specified to say 3 or 4 decimal places. So float 5 seemed reasonable there. Okay, so what we might do is just show you actually this segment. So what I can do is I can grab this point, and the segment has a length. Now the length corresponds to the difference in temperatures, bizarrely enough. And at the moment, the length of that segment is about 1.21, so that corresponds to 1.21 degrees. and it occurs at about t equals 7.8. But what we can do is we can grab the point. I want you to watch those two values there. We move it down to where we think that maximum difference is going to be. So the difference is increasing. Difference is increasing, and we get to about, say, there. That's about as close as I'm going to get. So the maximum difference, occurs at about t equals 3.9, and the maximum difference in temperature is itself correct to 1 decimal place is 2.4. This was craftily worked out because you've got to consider, you've got a 445 there. So to 1 decimal place, it's 2.4. Now, while what I just showed you is a nice demonstration technique, I don't think I would do it in the exam. Like, it looks lovely, but it might waste a little bit of time. So I was just showing you that more for understanding of the problem. Now, if we just went back really quickly to the wording of the question, nowhere in the wording of the question does it say that you have to find a derivative. So my sort of line of thinking, I write lots of exams in another jurisdiction and have been doing so for a long time. And my motto is, if you want to see something, you ask for it. Now, in this instance, the derivative, or d dashed of t, is not required. That's not to say that you can't use it, all right? But it's from the wording of the question there, it's not required. So a nice graphical approach would be suitable for this question, particularly when you see in code that answers are to be specified as decimals. So we go here and we say to ourselves, well, okay, we might do a derivative. Now, also, again, it's good to anticipate what's going on. So I'm expecting in a derivative to see something like -1 on 9 times t minus 12, and that could be expanded. And I'm also expecting to see something like a minus pi on 3 sine pi t on 12. So the shortcut for differentiation is shift and then the subtraction key. And so up comes the derivative template. The independent variable is t. And so we'll put in here dt of t. And that's what I expected. So that looks good. Okay. Now what we can do is we can find the zeros. So if we press menu, then 3 for algebra and 4 for zeros, and we can go up and grab our derivative. We need to find the zeros with respect to t, and we also need to add the domain constraint. So control equals, and if you go to the left, takes you straight to the with or the given key, and then we'll put in 0, and then control equals for less than or equal to, and then t, and then control equals less than or equal to 24, and we press enter, and they are our t values for the 3 stationary points. So you've got maximum, minimum, maximum, and we saw that from the graph. So if we go up and grab this and press enter, and then remove the 12 and also remove a comma, what I'm going to do is I'm going to add to these 2 t values the degree symbol, which for the moment is not required in the question, and you'll be wondering why I'm doing it. It's possible that a question might ask you for the time of day or the time in hours, minutes, seconds. Now, at the moment, my document is in radians, but if I use a degree symbol, that overwrites the radian setting. And then if I go to my catalogue, so you press the open book icon, and voila, you wouldn't believe it, that arrow DMS stands for degrees, minutes, seconds. So if we press enter to paste that into an entry line and then press enter, that's saying degrees here corresponds to hours. So that's saying that the maximum difference occurs in, if you think about the first one, t equals 0 corresponds to 6 a.m. So the first one would occur, for example, at 9:55 a.m. And 41 seconds. So that's a neat trick to be able to take a decimal answer and turn it into one that you can specify time in terms of hours, minutes, and seconds. Okay, our last example for the day is an example of integral calculus, and again, judicious use of the notes application. So the average or mean value of a function. So if f is continuous on the interval AB, so there's not allowed to be any breaks, there's not allowed to be any asymptotes, point discontinuities, etc., then the average or mean value of f on that interval AB is given by, now that AVE there in the subscript, so it's the average value of f is 1 on b minus a times the definite integral from a to b of f of x dx. Okay. These crop up most often in multiple choice questions, but don't discount the possibility of it being a 1 or 2 mark pass in an extended answer question. Here's the first example. So the amount of drug, d milligrams in the bloodstream at time t hours after it's administered is given by that decaying exponential. T goes from 0 to 2, and it asked to find the average amount of drug present in the bloodstream over the first 2 hours after it was administered and give your answer correct to 2 decimal places. So you can certainly do this in the calculator application. I'm going to use a pre-prepared notes application. Now, the point about this is that there's going to be an upcoming session on making notes applications and widgets and saving them. So stay tuned for that in this series. And the other thing is that you don't prepare them in the exam. That would be foolhardy. You have them all prepared beforehand. Now, the way I set these up is any parameters, I put them first. So we've got terminals or limits of integration A and B. So I've assigned A to be 0 and press enter. What you want to see is you want to see the blue input and you want to see green, in this instance, output. You want to see output because that means you've activated the math box. Okay, so I've got A is 0 and B is 2. I've, like a cooking show, I have already assigned f of t to be 2e to the negative 0.1 times t. So go inside there and press enter. Right, so that's done. Now what we want to do is we want to assign our average value of a function definite integral. So it's set up, ready to go, and we press enter, and that's done. So what this box is going to give us is it's going to give us the average value of the function over the interval from 0 to 2. It already knows that A equals 0. It already knows that B equals 2. It knows what f of t is, right? So that's all being substituted into there. And what's going to come out is a number. And so it's correct to 2 decimal places, a 1.81. And so if we go back to the context of the question, the average amount of drug present in the bloodstream over the first 2 hours after administered was, excuse me, was a 1.81 milligrams. Okay, so let's model what happens when you've got a notes page already set to go in the exam. So let's say in exam 2, you walk in and you see this question here. I'm obviously besotted with temperature. The air temperature in a particular suburb during a period of 12 hours can be modelled by that quadratic. T is measured in hours, W in degrees Celsius. Find correct to the nearest tenth of a degree, so that's 1 decimal place, the average temperature during the entire 12-hour period. So for our notes page, A equals 0, B equals 12, different function, and we should get, well, when I show you, you'll see how interactive and wonderful these notes pages really are. So what we'll do is I'll grab this, so I'll copy it, and then I'll go back into here. Now, remember that I need B to equal 12. So let's make that change now. You might notice here, even though it's not the right answer to the question, the bottom math box, the value will change, right? So you get an instant update. But what we want to do in here is we want to remove the exponential and we want to replace it with the inverted quadratic. And, well, you wouldn't believe it that when I pressed enter, the question is done. That the average temperature over that 12-hour period, correct to the nearest tenth of a degree, is 21.8 degrees Celsius. So I know that I'm talking to you and showing lots of different things, so it's a bit different to working in an exam. So I don't want you to think that this is slow. It's actually, once you've set things up and practiced and know how to access them and how to use them, they are quite quick. Exams are about accuracy and efficiency, right? So though, if you think accuracy and efficiency, then notes pages are very important for you. My final remark before I head off is you should walk into exam 2 with, notice here that I've got particular problems and pages. So this here suggests that I'm on problem 7 and page 3 of problem 7. So what I would suggest you do, for example, is if I go to this document, I've got a page here that's a calculator page, that's a graphs page, and that's a notes page. Then if I press doc and go to insert number 4, and then number 1 for problem, and then add a calculator, and then control doc, add a graphs, right? So I've got 2.1, 2.2, and then let's say I do that again. So press doc, insert a problem, and I'll add a calculator and control doc and add a graphs page. Right, so at the moment, what I've got is I've got 3 problems, right, denoted by the first digit. So if I go back through my record, right, so that's problem 1 consists of 3 pages. Problem 2 consists of 2 pages. Problem 3 consists of 2 pages. When you walk into the exam, if you're expecting, for example, 5 questions in exam 2, you should have a 4.1 calculator page, 4.2 graphs page, a 5.1 calculator page, 5.2 graphs page, and notes pages if you wanted to, 4.3 a notes page, 5.3 a notes page. Have your calculator already set up for the exam. The reason being is that each problem corresponds to a different question in the exam. And what happens is when you insert a new problem, anything that's been defined, assigned, or stored in any other problem is not available to you. So in other words, you start, when you start on a new problem, you're starting on a clean sheet, a clean slate. So you don't get mixed up with variables and parameters that have been used in other questions. I think that that's very useful advice. Okay, as is my wont, I've gone a few minutes over. It's been and continues to be a very difficult year for all of us. What I want you to do is to keep faith in yourselves and keep faith in the system. Continue to try and work hard. Practice lots of exam questions in the lead up to the exams. Ask your teachers lots of questions and prepare your calculators as best you can for exam 2, particularly in regards to the notes application and setting up for exam 2. We wish you all the best with your studies. Next week, I'll take you through some questions involving probability. So that'll be the binomial probability distribution and the normal probability distribution. Okay, so thanks very much. Have a good evening. Catch you later. Bye.